All right, thank you very much. It's my pleasure to be here today. My name is Eric Draeger, as was just introduced. I'm the Deputy Director of Application Development for the Exascale Computing Project. This is a large DOE project that spans many laboratories, but I will be calling out some specific issues that we at Lawrence Livermore have seen in addition. So one thing I want to say about the Exascale Computing Project is when people hear about this project, it's a big, expensive project, they assume this includes the computers, but it does not. So it turns out this is part of a larger project, and in this pie chart, I just want to call out the fact that on the bottom are the actual Exascale computers that are separate from us. So we have no control over what comes, but instead we are tasked with, once we know what that's going to be, helping many different applications use those computers effectively. So it's unlike the previous talk where there was a very intimate connection between the hardware and the applications, we are sort of at the mercy of what is chosen, and then we must just learn how to use it well. So just to give a sense of scope, this is a $1.7 billion R&D effort. It involves pretty much all the Department of Energy labs, which, even though I've worked in one for much of my career, I was surprised to learn there's 17 of those, and most of those labs are actually all involved in this project in some fashion. So you really have a very large effort spanning the United States where the researchers at the different labs are trying to come together to prepare for Exascale, which should give you a sense of how much we're worried about it, because it's a much harder problem than we've faced previously. And so just the number of teams is, we have over 100, and we have hundreds of top-notch researchers on this. So the way the project is structured, I'm going to speak specifically to application development. And that is, and I'll get more details into this in a second, but 24 HPC applications and multiple what we call software co-design projects. But we didn't want to just simply focus on applications. We needed to really think about the ecosystem and how researchers are going to use these computers in the future. So there were 3 parallel pillars that were set up as part of this project. The middle one is probably the most critical for application people, because this is software technology designed to help HPC applications use these new architectures and potentially future-looking architectures. So it involves software libraries, math libraries, very large-scale tools, runtime systems. So we're really putting a lot of research and effort into making sure that these core components will come along with us, and we don't have to hope that each vendor will implement everything we need when the machine arrives. And then we also have hardware and integration, which is researchers and experts who help work with the vendors and understand the specific mechanisms and the specific ways in which one would want to use a given architecture, and then translate that to the software and the applications in a way that we can use them without a painful amount of effort with every application. So this is our portfolio, and I don't expect you to read all this. The real thing I want you to take away is that we tried, the Exascale Computing Project really tried to capture a representative snapshot of the Department of Energy's diverse workload. So these are all important applications for the Department of Energy, and they span medical research, wind energy, nuclear energy, basic fundamental scientific discovery, as well as national security applications. And the reason that they did not try to capture every application that's important, because we didn't have enough money for that. But more importantly, what they wanted was, by the time this project is done, if you can get all 24 of these applications to use these new architectures well, that will basically be enough diversity in the types of workloads you're going to be trying to accelerate that other applications should be able to look at how we did this and then modify it for their own uses. This covers quite a few different strategies and mathematical approaches for doing high-performance computing. And in the rest of the talk, I'm going to give a few specific examples based on some of these applications on some of the strategies that are emerging for how to use not just the GPU machines that are coming now and the ones we know about, but to how to sort of prepare yourself for this cliff of uncertainty that we're facing as we look forward into what HPC architectures are going to look like. There's just so much uncertainty. We're really nervous about making guesses as to exactly what's going to happen. Now, this is what we call co-design, and based on the last talk, I'm hesitant to call it co-design because this is very much a software loop. We have there's sort of common algorithmic motifs that have been identified, and we have chosen 6 of those, and we have funded centers to develop software that is developed intimately in connection with the applications. And so, for example, our block-structured AMR, that center is being used by 6 applications in our project. And those applications are designing their codes around the software that this co-design center is developing. And this way, when the co-design center decides they're going to optimize their code for an AMD GPU, let's say, they only have to do that one time, as opposed to all 6 applications having to solve the same problem 6 times in parallel. So the goal is to create efficiency and to create a single point of contact for hardware vendors, for example, who want to know what can we do to help you make your applications run faster. However, it of course introduces sort of a dependency that we have to make sure we really manage so that the application teams don't feel that they could be in trouble if, say, down the road, one of these co-design centers stopped really supporting their use case. So we're really trying to create things that will endure. So these are the DOE supercomputers. Basically, before the project started up until when we expect the project to end in 2023. And the thing I want to really call out here is that we've had GPU machines throughout the course of this project, and in fact, our current crop of GPU machines over there in 2018, that's pretty much what we have as GPUs. However, up until now, every GPU we've had has been an NVIDIA GPU. And when we look at the future, we have 3 different types. So this, I mean, it's hard enough to write code for a GPU. If you've tried it, you already know this is not, if you have an existing MPI code, rewriting the whole thing to use CUDA is not an easy task. And now we have the issue that we don't 100% know which machine you're going to get the most time on or the most access to. And if you're a DOE researcher, you really need to be able to use the resources that are given to you. So you can't even write your code now for an NVIDIA GPU. You have to write it for any possible GPU. And this is where one of the reasons that the Exascale Computing Project was funded was to try and help researchers come up with some better strategies for dealing with these performance portability issues. So as I live near San Francisco, and we recently had a big bridge that fell down in an earthquake, and so it took us about 10 years to decide we should probably fix it. I mean, they fixed it so you could drive over it, but they didn't fix it so that the earthquake would not knock it down. And so when they decided how they were going to do this, one thing you realize is you can't just knock the bridge down and build it again. You have to figure out a way that cars can continue to go back and forth the entire time you're doing all this work. And this is really a good analogy for a lot of the codes we have in the Department of Energy. So these are codes that took 10 or 20 or 30 years to develop, and they validated them very carefully. They know that they're getting the right answer, and they're doing important problems that we need the answers to today. So we can't just take them offline for 10 years and rewrite them, and we certainly can't rewrite them heroically every time we get a new machine. So the key to us in this project is understanding that we need to put tools in place so that people can change their codes according to architectures as needed and make them usable on new architectures, but not take them offline. So the model of the bridge is still maybe not great because we don't want to build 2 parallel codes, but we still need to find a way to keep the code usable during the course of this project. All right, so now I'm going to start speaking to applications and what we've learned so far. And we're starting to see some strategies emerge. We've been reviewing the projects, all the 24 applications that we make them come and we do reviews, we talk to the PIs, and we see, how are you going to get onto these 3 different GPUs and make the code run on any number of platforms. And so you're seeing basically, I'm going to describe basically examples from the first 3 of these where you can just take, if you have a small enough kernel, take your kernels and rewrite it every time you're on a new GPU. So you write your NVIDIA kernel, you write your AMD kernel, you write your Intel kernel, and if it's like something like molecular dynamics where the force interaction is not that complicated for some cases, you can just do that. It's just easier to do that. And I'm going to give an example of where that's really been a good approach. You're also seeing for portability, people going to things like OpenMP and OpenACC for offloading work onto the GPU. It's very attractive in the sense that it should just work on everything. In our experience, it's been a little bit more difficult than that. And you also have overheads associated with the fact that every time you come to a loop, you need to maybe ship data over, do some work, and ship it back. So some codes are finding this to be very attractive, others not so much. And then a strategy that's emerging as a very powerful one is the C++ abstraction model. And this is, if you've heard of Cocos, this is the Cocos, and from at Livermore we also use something called Raja. And this is the idea that because as you get into more advanced C++ features, you can capture loop bodies as lambdas, and then basically send those off at compile time, depending on the architecture you want to target, to any number of code paths. So you can have one person on the Cocos team write your loop offload actual code for AMD or Intel. The physicist doesn't have to know anything about that, and that's very attractive to many, many teams. And lastly, is simply if you're an application, the co-design framework model where we fund co-design teams to do the work that under the hood, and then you just write the code on top of it. I'm not going to speak to this in much more detail, but it is another way to go, and it's essentially a sort of a library separation of concerns model. All right, so the first example I want to speak to is this is our EXA SMR code, the small modular reactor code. The PI is Steve Hamilton at Oak Ridge National Lab. Now, I'm not an expert on small modular reactors, so don't ask too many questions, but the basic idea here from the application development perspective is that you're coupling Monte Carlo neutronics with fluid dynamics, turbulent fluid dynamics. And so you have these two separate codes that have to be coupled, and both have very good performance. And of course, they're trying to scale this up to a very large system so that they can actually do design and reactor modeling. Now there's a picture, you probably can't see, of the assembly they're trying to build down on the right. Let's see, how am I doing on time? Okay. So this may be a little basic, but I want to just walk through what they found when they started thinking about the Monte Carlo piece of this code and how they're going to run it on a GPU. The basic problem is when you look at the NVIDIA, the GPU, this is a generic GPU execution model. The NVIDIA part just comes into the warp size, basically. But the idea is that just like with SIMD, you need to find groups of work that are basically all going to be doing the same thing so you can turn the crank on these things in parallel. And so in this case, we need blocks of 32 threads that ideally will be doing the same thing. Unlike SIMD, however, you can get away with having a couple of your threads do something different, and this is what's called thread divergence, where depending on the code path, you're going to, some threads will do one set of instructions and one will do another, and you'll have to do those sequentially. A key aspect of GPUs and accelerators in general is, of course, the fact that you need to overlap these executions or else you're going to spend a lot of time waiting on transfer, and so you need enormous amounts of concurrency. And this is one of the biggest challenges applications are having, is simply finding enough fine-grained parallelism to keep these accelerators busy. Now, there's tons of parallelism in Monte Carlo. That's one of the great things about it. But so you take you have bazillions of these neutrons flying around. But the problem is this application is horrible for this type of concurrency because not everyone is going to be doing the same amount of work. And so you have the issue where if you parallelize over particles, most of them, the vast majority of them are going to be in the far left of this graph here in terms of number of collisions they're going to do before they finish their path. But a few of them are going to live for a long time. They're going to continue going through that code loop over and over and over again while everyone else waits on them. And that's a serious problem. However, even if we didn't have that problem, even if every particle lived the exact same amount of time, this gets back down to the thread divergence issue because the physics of these collisions is going to change. You put in all sorts of options in your Monte Carlo simulation that depending on what happens to them at each step, they might end up doing evoking very different physics routines. And so you end up with a nice load balance work graph over there on the left where I've broken out the common code paths on the right, and you see it slows things down significantly. So after doing this analysis, what they found is that instead of parallelizing over particles, they should be parallelizing over these blocks of work. That's the only natural thing when you look at these accelerators. So they moved their Monte Carlo algorithm, just rewrote it from what's called a history-based, where you look at the history of each particle, to an event-based, where you look at what happens to each particle, and you parallelize over that. And so they got a much better result. Now, what I'm showing here, the graph is two different GPU architectures, both NVIDIA, and then two different systems which essentially had very different load balance characteristics. That's the fresh and the depleted core. So what you should see is on the left, starting from the history base, everyone's normalized to 1, and you'll see how much each system was able to be sped up with the different changes to the code. The most interesting thing for me here is that the first step was actually very unimpressive. When you actually get to event-based, you see a speed up. I mean, it's nice to get like a 2x or a 1.5x speed up, but it's not going to change the world. Where you really see the improvements is once you've done that refactoring, that's where there's real opportunities to use the hardware well. There was never really an opportunity with the history base. That was the best they were going to do. But basically, once they started doing the analysis on these new kernels, they realized, okay, we're just not using this particular hardware very well. I mean, we don't have good occupancy. We're not saturating the registers. So if we break up these kernels into smaller pieces, we actually can get much better performance. And this is where you see the huge performance gains. And that final step is really just having a final step of breaking up your events depending on where they are in the physical system, because you can find better load balance that way. So that's a case where the kernels themselves are just not very difficult to actually write in CUDA, for example. They're not very big kernels. So once you've done this analysis, write them in whatever language you want. That was their conclusion. So when they get to the AMD GPU, for example, they're not going to have any problems rewriting these in HIP. They can use just a little automatic tool that converts it to HIP, and they'll be good to go. But you have to really understand what's happening under the hood before it's even worth making those decisions. So now one that's very attractive to a lot of people is OpenMP. I want to give a call on an example where OpenMP is working really well, just because that's very encouraging and inspirational. And that is the QMC pack code. That's the quantum Monte Carlo simulation used for fundamental predictive material science. So in materials simulations, you know, we know there's all these hierarchies of materials of accuracy. This is at one of the lower levels where you're just trying to solve the many-body Schrodinger equation with a few modest assumptions. The nice thing about this is it's generally mapped very well to computers or to HPC architectures because it's very compute intensive. But the challenge with this is it's again a Monte Carlo application, but it's a Monte Carlo application that you can't get away with brute force because of the issue I'm showing on the left here. So unlike a sort of traditional Monte Carlo where you have these very simple particles that you're bouncing around and just gathering massive statistics, each of the ensembles here is actually a very heavyweight, compute-intensive quantum mechanical calculation. So you can accelerate it, by gathering statistics, that's only going to get you so far because you have to equilibrate each one of these very heavyweight populations. And if you use brute force, just more and more and more statistics by creating more and more and more copies, all you're doing is shrinking the right side, and then you're spending all your time in an Amdahl bottleneck on the left because you can't parallelize the equilibration by brute force. So what they had to look at was how can we better parallelize the actual calculation itself and no longer just rely on Monte Carlo to save us. And so they started from a very nicely parallelized code. It scales via MPI beautifully, as you can see on this curve on the right. This is actually on Summit, the newest GPU machine. But most importantly, they, again, had to do a detailed analysis on whether offloading these loops using OpenMP was going to be practical. And they did this using a proxy app, or a mini app, where they basically separated out a few key parts of the code, put it into a small standalone application, and then they could just take that apart and put it back together any number of ways just to try out a bunch of different strategies. And what they found, ultimately, was that while they were ready to go to something more advanced like Cocos or direct CUDA, OpenMP worked as well as anything and was much easier for them to work with. The physicists don't want to deal with very low-level computer science if they can get away from it. So they were very happy when OpenMP worked well. And this is actually their best result, and in fact, 3 times faster than the original CUDA code they'd started with. They learned enough in the course of analyzing this, they actually could write a better code in OpenMP than they'd started from in CUDA. So this analysis is really the key part of any one of these processes. But this result here is for a very large ensemble. 512 atoms in quantum mechanics is enormous. And that's so, if you have a huge system, you can, of course, get good performance. However, they often want to run not just capability mode, but also capacity mode, as Professor Sato mentioned. And when you run smaller groups of particles, the performance is pretty terrible. And so this is actually several different architectures. The lower is better in terms of this is time to solution metric. And so you see on the left, that's CPUs. On the right is 2 different GPUs. And all we're doing is basically the PI realized they needed to batch up work as best they could before they called these OpenMP offload functions. And this is just basically the effective increase in the batch size. And you see the performance immediately gets much better until you saturate, essentially, where it's big enough that you're no longer worried about the high cost of transferring data. So this is very encouraging. Again, if you just try OpenMP out of the box, you might say this is terrible. You're going to get that curve on the left. But make sure you're analyzing your code, and if you can make a proxy app to really understand where your bottlenecks are, there's a hope in almost any performance model or any programming model you're going to use. All right. So for my last sort of discussion of the strategies we're seeing in ECP, the C++ abstractions, if anyone asks me, like they're going to write a brand new code, I will tell them, write it in C++, use one of these abstraction models, your life will be easier, because someone else is doing a lot of the heavy lifting for you. And so the people who are doing the heavy lifting right now in DOE are the NNSA labs, our National Nuclear Security Administration labs, that's one of which is Livermore. And they have the hardest problem when looking at GPUs. These codes have been written for 30 years. They are absolutely humongous. They're multi-physics. They're used in a variety of contexts. And they just have millions and millions of lines of code that no one wants to rewrite. I mean, some of the code is written by someone who retired and maybe died. Like, you're not going to want to figure out what tricks he used, after the fact, if you can help it. So this is one of our big multi-physics codes called Marble. They've learned enough in the last decade that they're now moving to as modular an approach as possible, where they've separated out the physics packages into independent codes, every common component they can find in terms of I/O or mesh remapping, things like that. And so they're really getting a good separation of concerns, but they still have the issue that each one of these packages still has to run on the GPU and get reasonable performance. And so this is where things like Raja and Cocos are really critical. And I'm just going to quickly walk through how those work. Here I just want to call out the fact that Cocos is something of an all-in-one solution. And then that just was what made sense for Sandia Lab, who developed it when they started. Raja is a much more separated solution. So you have your execution code, which is Raja. You have your memory management code, which is what we call Umpire. And then you have a nice sort of toolkit for automating, so basically a smart pointer abstraction of managing memory and knowing when to transfer it for these arrays. Because depending on when you touch them in your multi-physics application, you can never know who's touched it last where. You really want a nice, easy way for physicists to not have to think about the bookkeeping of, is this memory on the GPU or the CPU? And so we have these 3 separate pieces, but they interoperate very nicely. Some of our applications don't use the memory side. They just use the execution side and handle the memory themselves. Others really get a lot of benefit out of that. So I just wanted to call that out. But the basic idea is very, very simple. Using C++11 and beyond features to do lambda capture, you take your loop body, the physicist just marks it up a little bit differently, and then once you compile the code, that's where the template work is done such that it pulls out the execution policy you've told it to use. That can be OpenMP, that can be CUDA, whatever you like. But the nice thing, too, is because we're abstracting the work, you can actually now think about abstracting how you iterate through the loop, depending, for SIMD architectures versus GPUs, you might want to stride through very differently. You could imagine breaking up the work into specific size pieces, reordering loops. There's quite a lot of options you can do. And this, again, allows you to, at compile time, do a lot of this optimization without having to touch the code itself. This is really important when you have physicists who do not want to be computer scientists adding very important new features, but you also want them to have reasonable performance. So you can have complete separation of that analysis and optimization work without getting in each other's way or stepping on each other's toes. And we found that to be a very effective model. And so I'm just giving some examples of as they're moving forward and developing these abstractions, things that they're finding really important. And the ability to permute and change orders of loops or break up or combine loops, this has been very critical in getting reasonable performance. And in fact, they've gone back and put this into existing multiphysics codes that were not being developed for the next generation. They're kind of our current workhorse codes. But because they're already C++ codes and they were able to incrementally update the loops one at a time without breaking the whole code, they've been seeing very nice speedups in these existing giant multiphysics codes that were never written with any idea of a GPU. So I've just given 3 examples here of seeing between 8 and 16x speedups over on a node-for-node comparison over a standard Intel Xeon node. So again, not the best speedups you'll ever see, but certainly much, much better than anyone expected. And even though we have these much nicer tools, we're still learning as we get to new architectures. There's always hidden, you fix one problem and there's always new problems. So for example, with GPUs, some of our codes have gotten to the point where the launching of these kernels takes all the time. And it's a good problem to have. It's because they sped everything else up. But you still want to keep improving. And so they've actually found that if they can stagger the launches, they can actually mitigate that. But that was actually, with one of our codes, a significant problem that for a while was really limiting their performance. And of course, no one's really surprised, but the memory allocation in the GPU and the movement of data between the memory spaces is a key cost that we just have to constantly stay on top of. And of course, this type of work, this multi-physics work, is a big challenge because you have to coordinate a lot of different efforts. And as we move more and more to big multi-physics calculations, you have to make sure people aren't hogging the GPU memory. It's been a big issue. All right, I don't really have much time here. I'm just going to note that our earthquake modeling code was able to, because they were at Livermore, they were able to piggyback on top of that multi-physics work by using Raja as well. Just a quick note that trying to do seismic modeling is a massive problem because you want to get to high frequency in order to understand the effect on buildings and structures. So they need to do very large, very precise simulations. These are a classic example of physicists who do not want to be computer scientists, but they saw a big speed up when they were just refactored their loops and worked with one computer scientist to get good performance in the GPU. So this really saved them from having to learn how to write CUDA, which they did not want to do. And because of this, they were able to do the largest earthquake simulation ever run on Summit, the new GPU supercomputer at Oak Ridge. A little note I'll say, I actually live in that little box, and their simulations really bum me out because my house is going to fall down. But we should know this, so it's good to know. But this is a real accomplishment, and it's really a sign of the effectiveness of separation of concerns. All right, so I'm out of time. I'm just going to conclude. The best thing you can do before you start refactoring a big code is learn as much as you can to make sure you go down the right path. We've seen efforts in the ECP where people have started down a path and realized it was just a terrible strategy. So the more you can learn from others before you get started, the better. Separation of concerns is a key issue, and a key way to do that is modularization. So find out where you can separate out things that need to be specific to your application and where you can reuse existing libraries and components. And actually, I have to say, as much as we all angst over how we're going to write our code, in the ECP, we're really seeing that if you care about performance, by far the most important thing is the analysis and the refactoring of the code around an accelerator-based model, far more so than the actual performance model or programming model you use. So again, getting back to the first one, just spend as much time as you can understanding and analyzing before you really start tearing it apart, because that time will come back to you several times over. Thank you very much.
Thank you very much. Questions?
So thank you very much for your presentation. But in particular, compared to the Recode approach, it seems that a lot of the effort, the thinking, and the cost for the code portation was on the software side. basically exclusively on the software side and on the software guys. Do you see any ways of pushing some of this effort a little bit more on the hardware guys?
We would love that. So the thing about them we're very jealous about of Japan is that they really do seem to have influence over the hardware vendors. However, all of our main hardware vendors now make so much more money off of video games and machine learning that us saying, build your GPU this way or build your CPU this way, it'll help us a lot and we'll pay you this much money to buy that computer, it's a drop in the bucket to them. So while we have had efforts to try and push more onto the vendors, and we certainly work with them, we're finding that as application people, we have to really just sort of rely on ourselves and look and see what's coming, but it kind of falls in our lap. And so it's a disappointing answer, but that's what we're seeing.
It's very interesting to see the two very different approaches from Japan and US. Other questions?
Yes. What is the difference between Hydra and Cocos? Because it seems to be almost the same thing, no?
I'm sorry, the difference between what?
Between Hydra and Cocos.
Yes. They have been merging. Actually, they're very much more similar than when they started. When they started, the big deal breaker for Livermore with Cocos was the fact that it had explicit memory management, so that you essentially had to either have all parts of your code use it, or you had to put in a lot of sort of shim code to fix up all the memory transfers as things got pushed to the GPU that you'd have to push back. Whereas Raja was written around the notion that we can do it loop by loop. One loop can be Raja, everything else can be not Raja, and you don't hurt your performance so much because you're keeping the memory as a separate concern. Cocos has since gotten a lot better about that. That's no longer an explicit requirement. At some point, I actually wouldn't be surprised to see them completely merge or even get pushed into the C++ standard. But they still do have some differences based on the relative priorities of each lab. But honestly, even though I'm a Livermore person, I'd say if you're going to use one of them, use Cocos. It's more widely supported, and it's much more widely used within ECP.
Over there, Nava.
Well, thank you for your presentation, but the third point, the third lesson learned, is a bit annoying. That means that any investment will be lost as long as the hardware architecture will change. So it's a very bad news for application guys.
So yes, and to be fair, I might be overstating it a bit. I would say the biggest effect right now is moving it away from a homogeneous MPI everywhere model to the notion that an accelerator and a heterogeneous memory space can exist. And if you can separate that out, the hope is that when the hardware does change, you have a smaller piece of code you have to change and modify and optimize for that hardware. But personally, from my experience, I've never found a code that because I've worked on many applications, every time we get a new computer, they always promise it's going to work pretty much out of the box, and there's always work you have to do. So I don't think it's ever going to be fully fixed, but the hope is that we can at least reduce the size of the code that you really have to focus on.
So it is realistic, but that doesn't mean that you pushing on the hardware vendors might also be an option.
We would love that. We've had very little traction, so maybe we can get Dr. Sato to come to the US and work with us to teach us how to do it.
We're pleased to do. Thank you.
You had a false example, a false way with co-design
Yes.
frameworks. Can you say a few words on it?
Yes, let me pull that up. So this is the basic idea of essentially the co-design, the software co-design code becomes a library that each application will build upon. And so, for example, in the case of the AMR, the adaptive mesh, what they're doing is they're essentially coming up with their own ways of abstracting that very specific type of work that falls into kernels that will be very specific to each GPU. But the thing is, they will write the CUDA kernel, they will write the AMD kernel. What you will do is call I'm going to do this type of adaptive mesh operation, and then under the hood, they will have solved how that'll run on the hardware. So it doesn't really solve the problem completely, it just takes it out of the hands of the application developers. So you still have a lot of work to do, unfortunately, you're just making someone else do it. So in the case of ECP, that's a very attractive approach because we can reduce duplication of effort, but for a standalone application team, that doesn't help you unless you're already doing one of these things.
Can you explain better, the difference between C++ abstractions and co-design? I'm not sure that it is that clear for me.
So the co-design is it's not so much a programming model, it's just a strategy that an application can leverage to run on a
Okay.
GPU. It's really, just think of it as a library, and however they
Okay.
solve it is up to them. And in fact, they tend to use a lot of C++ abstractions in those codes.
Okay. Okay, thank you very much.
Thank you.